So we've seen now how we can create the material conditional out of or and not, and we've also seen in an earlier video that we can construct exclusive or using and or and not. And we might wonder whether there are further truth functional connectives that we might happen to want, and whether we could construct them out of the connectives that we have. And this is the question of whether our connectives are truth functionally complete. The happy news is yes, and in this video we're going to see why. As it stands, we have 4 binary connectives, and, or, if then, and if and only if, as well as the unary connective not. And we've already seen a number of ways of constructing truth tables for other kinds of connectives we could have using just these. So for instance, in an earlier video we saw that we can construct a truth table for P or Q but not both. We might write this as P XOR Q, and this will have the following truth table. By logical equivalence, any 2 sentences are equivalent just in case they have the same pattern of T's and F's under their main columns. So the question whether or not we can construct any truth functional connective we want to is just reducible to the question of whether or not we can get any pattern of T's and F's that we want. Now there are 2 ways to do this. One is just to say, let's try using our ingenuity to construct as many as we'll need. Since it's binary connectives and since they can either be true or false, so they have 2 values, it'll be 2 to the power of 4 or 16 operators. We could just do it this way by constructing a bunch of truth tables and trying to figure it out. But actually there's a more interesting and elegant way of showing that our truth functional operators are complete in the sense that we can use these 5 to construct all 16 of these. Here's how. So let's take a star to be our new operator that we wish to define, and we want to show that we can make star correspond to any one of these 16 we happen to want up here. The way to think about this is not in terms of T's and F's, but more generally in terms of values. So we have the first value up here, the second value, the third value, and the fourth value. Now, if star were or, then we would have something like this. First value equals T, second value equals T, third value equals T, and the fourth value equals F. And that's just our truth table for or. Now, we've already seen a truth table that just makes the first value here true and the rest false. And that's the truth table for and. I'm going to erase this. So P and Q equals T on one and false for all the rest. Now let's make one that gets us T on our second here and false for all the rest. And that'll just be P and not Q. That's true on the second value and false in all the rest. For our third value, we have not P and Q. Since this will come out false in all the rest, except here where P is false, and so the not here flips the P, making it true, and then we have true, true. Finally, if we want to give one that is true in the last row, we can give not P and not Q, which is true in row 4 and false in all the rest. Suppose that we want to construct a truth table that is true in the first value and the third. Well, we just make a disjunction of 1 and 3, and that gives us P and Q, or not P and Q. And this will be true in the first and third rows and false in the second and fourth. So this is the one that we wanted. Alternatively, if we wanted to do first and fourth rows, we would make it a disjunction of, instead of this one here, the fourth sentence in our list, not P and not Q, and that will make it true in the first and the fourth and false in the second and third. So in this way, we can make any binary operator that we want out of disjunctive strings of these sentences. And this shows, at least for binary operators, our system is truth functionally complete. Now this doesn't get us every unary operator that we want, and it doesn't get us every n-ary operator that we want, but we can show that we can do this. Unary operators are easier, so let's just start there. So let's represent this unary operator we want by this hashtag symbol, and we'd say, okay, we've got true or false under P in our reference column, and we have values 1 and 2. If we want value 1 to be true and value 2 to be false, then obviously hashtag P is equivalent with just not P. On the other hand, if we want value 1 to be false and value 2 to be true, then hashtag P is just equivalent with not P. If we want them both to come out false, suppose we want hashtag to be our falsifier, which falsifies any input, then we can just treat it as equivalent with P and not P, and that will get us false on all values. On the other hand, if we want to turn hashtag P into the operator that makes P true always, so takes any truth value of P and turns out T, we would just treat it as equivalent with P or not P, which gets us TT. So much then for the unary operators, of which there there are 4. Not, 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 and then a further 2 which are equivalent with P and not P, and with P or not P. This is all well and good, but we want to generalize and show that we can construct any operator we want with any arity. And we can do just that. Let's start with a ternary operator which takes 3 inputs, and we can represent this with the symbol smiley face. Now we can pick any string of T's and F's we want to go under our main connective. If we pick this as our column under our main connective, then smiley face turns out to be roughly equivalent with if P then Q else R. And we can provide a disjunctive string of sentences that gets us each of the truth values we want, which we can of course number 1 through 8 here, the way we did with 1 through 4 above. So it turns out that smiley face is equivalent to P and Q and R, which gets us our first row, or P and Q and not R, which gets us our second row, or not P and Q and R, which gets us our 5th row down here, or not P and not Q and R, which gets us our 7th row right here. And the rest of these will come out false. So this disjunctive string on this side is itself just equivalent with our smiley face operator over here. And in general, we can construct any operator of any arity we like using this method. So the rule is, if an operator like tree, or like leaf, let's make this a leaf. If an operator like leaf expresses an n-ary connective, then it'll be equivalent to a disjunctive string D of sentences, C1 through Cn, where D contains Ck if and only if the kth row of leaf is true. So you can see that we did this here. With smiley face, we constructed a disjunctive string which is false in every row except for the one we wanted. That is to say, the first row, the second row, the 5th row, and the 7th row. And we can use this procedure to construct ever more complicated logical operators of any arity. But we don't need to do this by and large because we have not and or and symbols that we can derive in terms of them, if and only if and if then, as we saw in a prior video. So it's just reassuring to know that our Boolean operators are in fact logically complete. I want to end on something really cool that for me was really exciting when I first found it, which is the so-called Peirce arrow, which we represent here as a binary connective, a downward arrow between P and Q that symbolizes neither P nor Q. And what do you know? The Peirce arrow is actually complete. Now, since we've already shown that and or and not are complete, showing that the Peirce arrow is complete is just a relatively easy matter of showing that it can express and or and not. Let's start out with not P and see how we can express this in a Peirce arrow. This is just equivalent with neither P nor P. For our binary operators, we have P and Q, which is equivalent with neither P nor P in a neither nor pair with neither Q nor Q. Just to be clear, this one here is our main connective. Finally, if we want to express P or Q, we can express this as follows. Just to be clear, let's put this in a truth table, and that'll be how we conclude. Now, we've already seen the truth table for P or Q. We can write it pretty much from memory. It's true in all instances except where both of them are false. Let's construct our truth table on this side using the Peirce arrow. So neither P nor Q will be false where they're both true, and false where one of them is true, but true where they're both false. And this will be the same on both sides. But then our main connective in the middle here will be true in all instances in which both of them are false. So it flips these. And this is evidently just the same as this over here. So we've managed to construct disjunction using just our Peirce arrow. And if you're curious, I would encourage you to try running a truth table for not P up here or P and Q down here. Now, we're not going to use the Peirce arrow in this class because it makes things really complicated really quick in terms of how much it takes to write out. If we were going to study our system of logic, we were going to conduct meta logic, it would make things simpler because we'd have less to say about the connectors we have. We'd have to just prove things about one connective. And this might make you wonder, given that the Boolean operators are truth functionally complete, how many do you need? And the fact of the matter is there isn't really one answer to this at all. It would be needlessly laborious to use just the Peirce arrow for all the things we're going to be doing in this course, but on the other hand, it would be way too complicated to introduce a new operation for everything else we needed when we could just use the Boolean operators or the conditional signs. So it really depends heavily on what you're trying to do and how willing you are to accept more symbols into your system. Because metalogic is in the business of proving things about systems, and systems with fewer items in their language are easier to construct proofs about, in logic we tend to have fewer connectives. On the other hand, computer science, which uses logic gates to model Boolean operators, and actually constructs them out of transistors and so forth, has a greater incentive to introduce more symbols rather than fewer, because it's way easier to construct logic gates that way. And this, I think, is probably why the computer sciences have introduced XOR as a P or Q but not both operator, whereas in logic we've not. We're trying to prove things as simply as possible in terms of our language. The computer science is trying to make these things as procedurally or even mechanically simple as possible. And so that's why we have a relative paucity of symbols. But again, how many operators is the right number? If your operators are truth functionally complete, there isn't really a right answer to that question. And you could certainly make a case for adding more or taking certain out of the language we're developing here. And with that, we've wrapped up week 9. Now, there are some important considerations about conditionals that we've glossed over, and in the future I plan to make some videos about alternative ways of reading the conditional that aren't quite the way the material conditional works. These will be optional, of course, but it touches on some philosophically interesting things. For now, anyway, this is the end of the week, so good luck with everything, and let me know if you have any questions.